in this lecture, we are going to discuss one more characterization technique, surface area measurement using gas adsorption isotherm. Okay, so we have discussed transmission electron microscopy, we have discussed Raman spectroscopy, and we have discussed also X-ray diffraction. These are some of the very important techniques for carbon materials. So these are the techniques that are essential, that you must know. That does not mean that there are no other characterization techniques. That will depend upon exact application that you have and exact type of carbon material that you're using. So for example, if you want to use the magnetic property of a certain carbon material, in that case, you will require a completely different set of additional characterization techniques. But these are the basic things you will always use, because crystallinity is always important, especially when we are talking about graphitic carbon materials. Crystallinity is always important, and for that we use X-ray diffraction, Raman spectroscopy, also TEM at some point. We also use scanning electron microscopy. Maybe briefly I will discuss it here as well. So these techniques we definitely use. Now, when does surface area become very important? Well, when we are dealing with activated carbons or other types of porous carbons, or when we are dealing with carbon black. So if you remember, we have these fluffy carbon black particles. When something is fluffy, that means there are some pores. And then we need to somehow measure what is the surface area. By the way, surface area and porosity are very closely related. They are not, however, it's not that every time you induce porosity, you will have surface area increase, because as the name itself suggests, it's just the area. It's a 2D thing. So what you're doing is, if you're inducing some sort of volume porosity, it will enhance or increase the surface area if and only if your pores are reachable from the surface. If it is closed porosity, so you already have an impression of the closed porosity. Maybe I'll also describe a little bit more. So if your pores are closed, in that case, it will not really reflect in your surface area measurements. Okay. But in general, if the porosity is increased, often it happens that the surface area also increases, especially in the case of activated carbons, because you have, often a lot of pores are connected, percolated. Okay. So the pore dimensions, that also, if you remember that we talked about these fractal-like geometries, which means you have larger pores, smaller pores, even smaller and smaller and smaller. So you have also the porosity very nicely distributed in porous carbon materials. Actually, this is also a very interesting subject for surface area measurement, because when you increase porosity, sometimes it's just one type of pore that the number of these kind of pores or fraction of these kind of pores that increases, and sometimes it's the fraction of all types of pores that increases. That would depend upon your activation method, and that also depends upon the type of carbon it is, whether it is formed by the charring process, whether it is formed by the coking process, or whether it is a very highly graphitic material. Depending upon all of these things, also the physical structure of the material. For example, are you activating carbon fibers, or you're activating something in bulk, or you have a well patterned structure, let's say micro nano scale structure, and then you're trying to activate it. So it will always have just a different pattern of porosity altogether. And should we be, so the idea is that, should we only be able to measure the net surface area, or is it also possible for us to know which types of pores do we have? Are these small pores that are increasing, or the larger ones that are increasing? So you know that both are important for us. Okay, so we'll see how we can do that. First of all, this is the image again from this activated carbon lecture. So you remember these pores. These are the, what is it called? These are called the fractal-like geometries. Okay. Now let's say this was a piece of wood. It also had, let's say it's a branch of a tree. It had, on the top surface, it had some pores, and now also on the bottom surface, there are some pores, right? These may be smaller, or they may be of the same size. I have just drawn them. Okay. You may also have some pores in the middle which are not reachable, which are not connected to top or bottom pores, and these are the ones that we call closed pores, right? So basically, irrespective of the geometry of the pore, whether it is spherical or not, doesn't matter. As long as it is not reachable from the top or bottom or any open surface, in that case we call it closed pore, otherwise we call it an open pore. Okay. We also have carbon black particles. So here I have shown this porous kind of carbon particle. It doesn't have to be carbon black. It can be other forms of carbon as well. But the idea is that you should have then very small crystallites, very small turbostratic crystallites, and a lot of space between them. In that case, the porosity of these materials also becomes important. See, porosity also is directly in relation to absorption. In fact, that is the principle that we are using for the measurement of porosity, which also means that if you want to use certain carbon material for absorption applications, in that case, their porosity is very important to you. Okay, so that is the reason we measure the porosity. Okay, so some common techniques. I will first tell you, a number of techniques that are used, and some of them are more common than the others. The one that we are going to discuss, gas absorption isotherms, is the most common technique. Now, of course, using that technique, you cannot get the information about closed pores, and you cannot even get very accurate information about surface area, which I'm going to discuss. However, you get a very good idea of the surface area. Also, if you want to make comparisons, so for example, if I have two types of carbon materials, one I have just taken as the sample itself, and then the second one I performed some activation. On the third one I performed even more activation. What do you mean? This means that you're inducing more and more porosity. Of course, also chemical functional groups, but in some cases, but you're inducing more porosity. So in that case, I can definitely get a relative value of how my porosity is increasing and how effective is my treatment method. So this information may not be very, very accurate. Like if I say my whatever is the number of my activated carbon surface area, maybe it is slightly more than that. Or maybe even it is slightly less than that. Maybe some pores could not be reached. But at the same time, I get a more or less accurate information because at least to understand my fabrication process, this is very important. This is very useful. Okay, so the first one we are going to discuss, gas adsorption isotherms. What is adsorption? It is just a surface phenomenon, right? So adsorption means that something is going and sitting on your surface. So some molecules because you see it is written in gas adsorption. So some gas molecules will go and get physically adsorbed on top of the surface of your carbon material. So they go sit there, and somehow we need to measure how many molecules are going and sitting there, right? If this is a flat surface, then the number of these molecules will be less. If this is there is more surface area, more molecules will go and they will go inside these sites or pores. If they can go far inside the material, then you can also then there are even more molecules that are going inside the material, right? How do you measure that? Well, one easy way to measure that is that you observe the change in the pressure of the gas, the partial pressure, because that is very much possible. So the equipment that we have, I'm going to show you a schematic on the next slide. These equipment basically utilize the gases, inert gases, in most cases nitrogen, or argon also in the case of carbon. Here and there you see argon. So you will have these inert gases which will go and sit on top of the surface on the sides, okay, on the porous carbon sides, and then you will basically measure the difference in the pressure, initial pressure. So this is the relative pressure that you are measuring. Okay, why do we choose inert gases? Because we want to make sure that the adsorption is just physical and not chemical. So the gas itself should not react, because if there is any attractive force when it comes to whatever your porous carbons or any other materials, also not just carbons, will also have some surface properties, and you do not want your gas itself to start reacting with the surface properties. Now, in some cases, you will also use carbon dioxide. You will also use you may here and there also utilize the property of chemical adsorption, but then you need to be very specific. Then you are actually, what are the surface groups on your surface. You are also confident that they are evenly distributed on top of your surface, and then you also can actually use some chemical adsorption. But in most cases, the physical adsorption is what is used. Also, the molecules of whatever gas you're using should be small enough so that they can go all the way inside. Because you may have very small pores, smaller than 2 nanometer pores. In fact, there are a lot of pores that are smaller than 2 nanometer. So in that case, you should also have gas molecules that are small enough. Okay, so this is something we are going to discuss in further details. Before that, let me tell you about the other techniques, at least well-known techniques. Mercury porosimetry. So I will not go into the details of this technique, but this is basically something that is used for large-scale pores. So when you have macro pores, for example, or mesopores. In that case, you typically would use mercury porosimetry. As the name itself suggests, there is mercury involved in it. And so I will not go into the details. This is yet another technique. SEM imaging. So we talked about TEM. SEM, how can we use that? So SEM image, basically, let's see if I have a picture. Yes, I have it here. So SEM image of porous carbon, you can see, will only tell you about the surface, right? Now what you can do, anyway, so number one, you should know that you will only know about the surface and not about, if your pores are cylindrical or how, deep down do they go, and also whether or not your, pores in the middle of the material, let's say, are connected to the top layer. So you'll only get the top view if you take this kind of standard SEM image. And then you will see that there are some pores. Now, based on the contrast in this image, you can actually perform some image processing, and then that will give you some idea of what is the volume or what is the surface that is covered by the pores, not volume, surface, because right now we are talking about 2D. You can extrapolate it to volume. And I'll also tell you a trick what will help you understand the volume porosity. But with this image, what you can do is you can plot your own histogram. So you can also perform the image processing using some software that is available nowadays. There are a lot of software that are available, free software. So you can basically use them and you can just, upload your image and calculate the porosity. But that is not something that is something I don't recommend, not just for SEM or image processing, but for anything. Even gas adsorption isotherms, you have an equipment, you upload your sample and you may actually get some data from it, some numbers from it. But you need to know how exactly the isotherms were interpreted. So interpretation of anything you should know. Only then you can get accurate values and reproducible values. Also, same thing for image processing. You will see, if you plot your own histograms, you will see that even by changing the parameters slightly, you may actually get different values of your porosity. So that is something you need to learn. Of course, if again you want to just get a relative value, so if you keep on performing certain activation, you want to just get a relative value, then you can also just directly do it using SEM images. So I was saying that you could also see the volume porosity. Can you think of something? How can I, if I want to see inside the material, let's say I have a film. I have a film of some carbon material, and this is a porous film, and I want to see what is the porosity. So right now I have just taken this image. Now if I want to see the cross section, the film is very thin. So I want to see the cross section of this very thin film. Let's say it's 50 micrometer. Now what I can do is, SEM machines typically allow me to tilt my sample a little bit, but only to a certain degree. Okay, so, and also your sample depends, it might be very fragile and so on, and it depends also how nicely cut your edges are. So what you can do, you can make some kind of, so if you take two, just a second, so if you can take two structures and you can take two, for example, some rigid material, for example, a silicon wafer also, you can take two silicon wafer and sandwich your thin film between them. Okay, and then accordingly you can cut it with a diamond saw, and then take the cross-sectional image. So this is also something that is a little trick you can use. Diamond saw will induce some defects, but it's not that bad, because anyway we are dealing with porosity and not microstructure right now. So if you want to get at least the information about how deep your pores are and whether or not they are cylindrical, that kind of information you can get by this kind of cross-sectional imaging. Okay. What else? So yeah, the other things that we have here is X-ray microtomography, or micro CT, which is the commonly known term for this technique. You already understand X-ray imaging. So X-ray imaging is the same principle that, if I take the image of my bone, it's pretty much the same principle. The only difference is that now we are taking an image at a micro scale. So the sample size is much smaller, and also what we are doing is now we are using a carbon material, often elemental carbon. It is challenging for carbon material. Performing micro CT is challenging, and why? Because carbon materials have very high transparency to X-rays, so it is challenging to get a reasonable contrast in the image. But this is also one technique that has been tried out. What else? I have also written magnetic resonance imaging. So again, MRI is a biomedical imaging technique. But you can also use carbon materials. Carbon materials are generally, they do not often cause too much artifact or anything, because you see the NMR active or MR active carbon isotope C13 is only 1.1%. So that does not really interfere with your imaging. So you can actually perform imaging using MR techniques. But at the same time, there are certain challenges involved there also, because you may get, for example, some air bubbles trapped inside your structure. Air bubbles can cause a lot of artifacts. Air bubbles often can be seen because you will, in the case of MRI, you will often have some maybe liquid, let's say heavy water, filled inside your structure, and then you will try to image it, and that is really challenging because of the presence of air bubbles. But this is also one technique that has been tried out, and I have shown also one image of porous carbon. If you remember, this image I have shown you also before in some lecture, now I don't remember, but this is basically a 5 millimeter. So you see in the inset, this is a carbon, sort of porous carbon structure which has a 5 millimeter diameter. Okay, so these kind of structures then you can image using MR also. Okay, so now coming to the gas adsorption isotherms. So again, you know what is adsorption, and we also now know that we have an inert gas which is getting adsorbed, and what we are doing is we are measuring the partial pressures. So this is what I have written here. These basically are the plots of the relative pressure versus the amount of gas adsorbed at equilibrium. So important term is at equilibrium, because this is a highly dynamic process, the adsorption of gas molecules on top of certain surface, because these gases are very dynamic. They're moving, the molecules are moving at all times, and the frequency of their movements is actually very high. So at any given point, you do have a lot of gas molecules being adsorbed on the surface of the structure and also leaving the surface. So equilibrium basically means when we have the number of adsorbed molecules and the number of molecules leaving the surface equal. That is what we call equilibrium. So at equilibrium, the value of the partial pressures that you will get if you plot it against the concentration of the gas or the amount being adsorbed. In that case, these plots are known as gas isotherms. So here I have shown a schematic of the equipment that is typically used. So one important thing here is that, okay, there are a lot of valves, and there's some detector, and there is a sample holder and so on. Important thing is that you have liquid nitrogen filled around your sample. So liquid nitrogen, why you're using it here? Of course, you're using some gas also for adsorption. So it can be nitrogen, it can also be argon, helium, but you also have the liquid nitrogen temperatures maintained when you're performing this experiment. And why? Because see, this is a very dynamic process. I already told you that it's to minimize the movement, the motion of the molecules. We have to use very low temperature. So liquid nitrogen temperatures are used for this purpose. Okay. So yeah, these are the things that I already told you. That adsorption is highly dynamic process, and in fact, also what we want is essentially a physical adsorption, but it is also possible that here and there you will have some chemical adsorption or some because activated carbon, let's take the example of activated carbons, they have very a variety of functional groups, surface functional groups, that would depend upon your activation method. So there is, although they will not form chemical bonds with the inert gas at that given temperature, but there can be some sites that are more active than the others. So there may be some not chemical absorption, but there may be some sites which are more open to absorbing something than the other sites. So what the values that you will get is not necessarily accurate. Okay, fine. So we use low temperatures, of course. One more important thing is that, if you remember, we talked about monolayer and multi-layer adsorption. I think again it was the activated carbon lecture. What is the monolayer adsorption? Now from this picture you can see it can become more clear that you have only a single layer of gas molecules adsorbed on top of your surface. But will that always happen? Well, that is the ideal case, and that is the assumption that we have made. But this may not always be the case, because you will often have multi-layer adsorption, because see, your gas molecules are also interacting with other gas molecules. Your gas molecules are also interacting with the carbon molecules and also the surface functional groups. So there are multiple molecular interactions going on, and that is why you will often have multi-layer formation. But we assume that this is a monolayer adsorption. In any case, for the relative values, it is fine, because if I take 2 or 3 or 5 carbon samples, just with varied porosity, in that case, if the monolayer is forming on one sample, then it's also forming on another, or the multi-layer. So in that case, the relative values you will get are more or less accurate. Okay, fine. So we also another assumption is that we assume that there is no adsorbate interaction. So this is the assumption we have to make in order to calculate the surface area. Okay, closed course I already described on the previous slide. So how do we now calculate the surface area from these isotherms? So isotherms, maybe I have the pictures here or on the next slide maybe. So isotherms are some sort of plots, and now you need to get the values of your surface area. You know that what we are doing is we are plotting pressure, so you're going to have some pressure terms when you want to calculate the isotherms, or when you want to calculate the area from the isotherms. There are several calculation methods, and what I have written 3 equations here. So the first one is known as the Langmuir equation. The second one is BET equation. This is the equation which is most commonly used. In fact, often you will also hear BET surface area analysis for carbon materials. So this is commonly used for carbon materials. Okay, and then you also have another. Actually, there are multiple methods of calculating surface area from the isotherms, and the other one is also Dubinin-Radushkevich. This is also something. This is a method that is used for calculating often not just carbon materials, but also in the case of liquid adsorption isotherms, this method is commonly used. Why do we use different methods? That depends upon your material and also the gas that you have used, and also the type of porosity that you're expecting. Sometimes you can even calculate you can use the same isotherm and calculate the porosity using all 3 equations and see what happens. Are you getting the same values? Because so now here I have written all the terms. So there are P and P0 are your different pressure terms. Okay, equilibrium pressure or the saturation pressure. And then also in these equations, what you see, the first one, if you see, it has some term called Na. Okay, Na and NaM. That is one term in this equation. Second equation, if you see, again, you have the pressure term, that is common, but instead of N, you have a V term now. So this is a volume term now. Okay, and in the third equation also you still have a P, but you have E, which is some energy term now. The idea here is that we are pretty much calculating the same thing, but the only the units differ. Now we don't calculate the the adsorbed gas in terms of volume, but rather the overall quantities. So that is why very important thing is that the units. So in all cases I have mentioned the units. Because even if you don't understand the exact name, whether it is volume based or whether it is what do you mean by quantity and amount and all of that, what the units will make it clear to you. So in the case, for example, of Langmuir equation, you have millimole per gram. That is your unit of calculating the monolayer capacity. Monolayer capacity means how many molecules are adsorbed on the monolayer. Okay. So similarly, in the case of your BET equation, you have the calculations in terms of volume. So this is the only thing that differs in all of these calculation methods, but you can typically use anything. And of course, you will also there may be certain methods where you will get more accurate information using one of these 3 things, because in all of these equations also you will have some constants. Okay. The third one, actually, the DR equation, there you see this energy term. This is also calculated based on the characteristics of your material. So what you will actually see, you will actually assume is that there is some standard adsorbate for every type of material, and the characteristic and energy of adsorption of that particular standard adsorbate is what you will take as the value of E0, and beta is constant, then you will calculate the value of E. So you will also need to know some of these constants and parameters. Also the value of C, I have shown how to calculate. C is the constant in BET equation. Okay, so the point is that you need to also then understand if you are using the DR equation, you need to know what is the standard adsorbate that you'd like to use. Typically the one that is taken for carbon materials is benzene. Okay, so these are the different calculation methods. So I will not go into the derivation. Actually, these are very simple derivations also. So just change in pressure based on the number of molecules that are being adsorbed. The number of molecules can be number or volume or the mole fraction. That is the only difference. Okay, so you need to also see the chemical structure, physical structure, all of that, and then you accordingly you can select your calculation pathway. Okay, so here I have shown some different shapes of the isotherms. Different shapes, you will actually, there are many different shapes that you can observe, but these are the common ones that you will observe, especially for carbon materials. See the third one as well. One important parameter that I want to tell you here is that what we get from our gas adsorption isotherms are discrete values, and then we often plot these lines. We are actually fitting the curves. So there is some information lost during the fitting, because the pores are not really continuously increasing. The number of pores is not continuous. It's not that you have 2 nanometer pores and then 3 and then 5 and then all the way up to several micrometers. It's not like that. Usually you'll have certain types of pores, let's say 2 to 5 nanometer or below 2 nanometer. You will have a bunch of these pores, and then nothing for some time, and then a bunch of slightly larger, let's say 30 to 50 nanometer pores, and then a bunch of macropores. So this is also, you can understand it from the fractal geometries, right? So you don't have a constant increase in the pore size, a linear increase. So you rather have 3 or 4 different regions which you will get in the adsorption data. But often when you already plot the isotherms, especially if you're doing it using computer software, then you may lose that information. So it will be good also to have a look at the raw data. That will give you better information. What is the region where you have more pores? Okay. Yeah. So this is what I have written here. Pore geometry is very difficult to calculate from the isotherms, because again you cannot guess whether these are cylindrical pores or what exactly is the geometry of your pores. In fact, sometimes what can also happen is that the number that you get for surface area from very different materials or structures can also be the same number, because then it depends. If that doesn't tell you anything about the pore shapes and sizes, right? If I have these circular or hemispherical type of pores, or I have cylindrical pores, or I have fractal-like pores, what I'm calculating is just the number of molecules that are adsorbed. So it is very difficult to calculate the pore geometry. Of course, the closed porosity you cannot guess from here. By the way, from X-ray tomography and MRI, although these are techniques which are challenging, but the advantage of these techniques is that you can also get the information on the closed porosity. So if you you have slices of images. So basically, when you take the MRI of your brain or X-ray of your hand, you don't have to cut open the brain, right? This is a non-destructive imaging. So that is why these techniques are very useful. These are non-destructive techniques that can also give you the information about closed porosity. So if your material has a lot of closed porosity, you might want to try one of these techniques. Okay. Fine. What else? You have different functional groups. You also have what is known as different thermal spikes. So at different positions of your samples, you may even have certain temperature gradients. And that is why, although we are trying our best to ensure that we don't have these gradients, and we are trying to minimize the temperature or the molecular motion by using the liquid nitrogen and so on, but there are possibilities of having even minor thermal spikes can change the adsorption behavior locally. So there are various parameters actually that can change the local adsorption behavior. You can also have if the porosities if you have these fractal-like structures, maybe sometimes the gas molecules cannot go all the way inside, through inside all the pores, and there are some parts of the molecules that are blocking some other pores. So there are definitely there is a possibility of errors, and that you need to understand for your particular material. Okay, so now here I have mentioned some resources for further reading. These the first one is a book, and from there you can get also a lot of information specific to carbon materials and the surface area measurements of carbon materials. So also the second one is the paper from where you can get the information about the origins of the BT theory. So there can of course be several more resources that you could utilize. Okay.